So welcome to those of you who've joined us and to this webinar from the Engineering Integrity Society. I will now hand you over to today's host, David Enzer, for a quick introduction to the EIS and today's presentation.
Hi there, everybody. Welcome to this presentation. It's from the Aircraft Research Association. They have a very good presentation here on force measurements on wind tunnel testing of advanced aerospace applications. I'd like to tell you first a little bit about the EIS, if I may. We are a well-established society now. I've been a member since 1983, 1984. It was started by Peter Watson many years ago as a forum for engineers to get together. We have four main groups: a simulation, test and measurement group, which I'm part of, and this is part of the presentation today. The durability and fatigue group, we look after fatigue and durability, obviously, and materials. The sound and vibration and product perception group, who deal with ergonomics and such like of the vehicle, especially noise. A very progressive little area that we've got now is for the Young Engineers Forum, which is a good forum for young engineers to get to meet and deal with lots of other people. We are sponsored by a large group of companies. You can see here, I won't read them all out, it's too many to mention. But also today, today the Aircraft Research Association are also a sponsor company, and we're really pleased to have them here and doing a presentation for us. It's always good when our sponsors and things also look after us. We do a lot of events like webinars, seminars, exhibitions and so on up and down the country. There's one coming up soon, which is a seminar on battery and design testing. It's at the University of Warwick. We also have our annual, well, we've just had our annual exhibition, which was in March at Silverstone, and there's another one next year. And we do a fatigue conference every year, which is very well attended. It's a big event, and that's at Jesus College in Cambridge. If you want any more information, obviously get in touch with the EIS, but all of the events are recorded. This one today will be recorded, and it will be available via that link on YouTube and also via the Engineering Integrity site. So without much more, I think we'll get on and talk about the presentation. ARA is a research association on passenger aircraft and all those sorts of good things. They work in close cooperation with Rolls-Royce. And today's presentation is about wind tunnel testing. It's about the development of force measurement in quite an advanced and quite a clever way of doing it from the bit that I've read. It's very good. There are three presenters today. I'm going to apologise already for my pronunciation, but is it Hoda Bedwi?
Bedoui, yeah.
Bedwi, lovely. Is a senior aerodynamics engineer, MSc in advanced computational methods from Imperial College. She leads an aerodynamic and structural analyses for multiple wind tunnel models and rigs at ARA. And there's, following that, there will be Manjit Ubi, who is a senior instrumentation engineer, man after my own heart, with extensive expertise and experience in all aspects of strain gauge installation, including consultation, planning and installation. But the one thing I'm interested in here is thermal optimization. And then there is Simon Lawrence, who's principal aerodynamics engineer. His MSc is in aerodynamics at Cranfield. Highly experienced in design and delivery of complex wind tunnel tests, and has been a technical leader of grant-funded research projects. He's also an expert in developing the use of bespoke force measurement balances. Really interested in this one. I'll now hand over to the team and let ARA get on. Thank you.
I'm going to start the presentation now.
Okay.
No, I didn't make it. Oh, yeah, it's here. Yeah, great. Yeah. Okay, good. Sorry. Of course.
Okay, good afternoon. I'm Simon Lawson. I'm an aerodynamic engineer at the Aircraft Research Association Wind Tunnel. So ARA is a wind tunnel, and this is going to be talking about force measurements on wind tunnel models. So on the screen now, you should be able to see an example of a wind tunnel model. The red area is the area over which we're trying to measure the forces, and a wind tunnel balance is used in that to do that measurement. So for this particular test, the main aims were to measure thrust and discharge coefficients. In order to do that, we have to measure the forces on the engine nozzle and the air pressures in and around the nozzle. And this requires a special force measurement sensor, which we call a wind tunnel balance. Another example of a wind tunnel balance is in the top right photo. This is what we call our 53mm diameter balance. And this would be used in that aircraft picture on the left, top left, which is our high-speed reference model. And that would measure 6-component overall forces and moments on the complete aircraft and would be mounted inside that aircraft. You can see in the table the design loads, so it goes up to quite high normal forces of 18,000 newtons, and the accuracy is very tight, so the target is less than 0.1%. At the bottom of the screen you can see the wind tunnel balance that I'll be talking about today, which is for our dual stream jet propulsion rig for blown nozzle tests. And the key with this one is that it has to have air flowing through the middle of it, which adds more complication and difficulty. So this is the design of that balance. The blue box on the left-hand side of the sketch shows the actual balance, and it's split down the middle, such that the left-hand side is the earth part, and loads are only measured on the live part, which is on the right-hand side, which includes all the green parts. At the same time, you've got flow going through the balance, through the middle as the core stream, and also in an annulus around the outside of the core called the fan stream. The balance requires some flexibility in order to work. So in order to allow that, there's bellows systems, which are these zigzag areas in the top and the middle and the bottom, and that allows the balance to flex, which is necessary to be able to measure forces on it. There's also measuring temperature, which is important to correct for the temperature effects, and we aim to get force measurements to below 0.2% in thrust. So we have to measure pressure effects, so we pressurize the balance and measure the tear effect due to that, and the bellows allows the air to flow through the balance without interfering with the balance structure, and also allows it to flex. We also are very interested in thermal effects because the air going through this, in this case, is very cold, so there are temperature gradients across the balance, both physically over space and in varying with time. And the temperature is a very important measurement to be able to correct for that effect. And my colleague Huda will be talking about that in a little while. The balanced instrumentation has to be installed to adjust for the changes in steady state temperature as well. It all has to be very robust because the wind tunnel is a very expensive facility and you need to be able to run it for long periods of time without failures of the instrumentation. There's a lot of complicated wiring and instrumentation that needs to be installed. And also we have to avoid something called hysteresis, which is where you apply a load and reduce and take the load off and you get a different answer. So we have to make sure all the joints are very carefully designed and there's no linkages between live and earth that might cause a problem due to that. So now I'm going to pass you on to my colleague Huda, who will talk about the thermal effects on this balance.
Yeah. So I am Huda Bedewi. So I'm a senior aerodynamic engineer at ARA. My main job is to simulate, to perform aerodynamic and structural simulations for wind tunnel models and rigs. So we will talk first. I will introduce briefly. I will make an introduction, and then I will talk about the balance thermal correction methods that we are implementing for balance thermal corrections. This method will be applied on a test case, and then introducing I will make the conclusion. So wind tunnel balances have a number of strain gauges, and ideally they should only measure the applied aerodynamic load. However, the strain gauge also responds to changes in temperature, which affects the strain measurement accuracy. So actually the temperature are the most common causes of error in strain measurements with strain gauges balance. So here at ARA, we have empirical methods to minimize sensitivity to temperature, like balance calibration, gauges layout optimization, and so on. However, the conventional empirical methods don't remove the thermal-induced strain error completely. So that's why here at ARA, we have developed a novel numerical thermal error reduction technique in order to reduce the strain induced by the strain temperature and changes. And the good thing with this method is that it is computational cheap, and it provides live thermal correction during the balance operation in the wind tunnel. So it's something we need a quick insight of the thermal behavior of the balance quite in few minutes, quite instantly. This balance you've seen here, you can see on the screen, that Simon introduced earlier, and we call it here also Avant balance. And this balance has these material properties here shown on the table. So it's made of Bramax AHH with the following material properties. So to correct balance measurements due to the thermal strain, we need to be able to describe the thermal behavior of the balance. And this means that we need to solve the heat equation. So this is defined as follows. So we have in this equation, we have the heat capacity matrix, the conductivity matrix, we have the temperature vector, and the applied load on the balance. So this equation is very expensive to solve as it involves complex matrix algebra. So as well as it's computationally expensive, it's also time consuming. So this to solve this equation, it takes quite a long of time. So, and in the wind tunnel, we need a rapid insight of the thermal effect of the balance, and in order to correct the balance readings quickly during the balance operation. So, as I said previously, within few minutes. We could say, yeah, why not having lots of temperature sensors on the balance? Yeah, but it's not really, technically it's not really possible to have thousands of temperature sensors on the balance. So one way to achieve, to describe the thermostat of the balance is to approximate the balance thermal and structural states numerically. And this new technical method, by approximating the thermal and structural state of the balance, will be able to give us a rapid insight of the thermostat of the balance and predict the thermal strain interfering with the balance output readings. So let's see a test case here. So due to a lack of experimental data, I use an FE analysis in order to check, test, and compare my data against the method against this, the FE simulation. So on this balance, so we have the Avant balance here. So on this balance, I have a number of temperature sensors, evenly spaced. There are strain gauges placed on either side of beams. So a beam is what you have in the red box illustrated here. And for each beam, we will calculate the beam strain calculated from 4 strain gauges. So it's about an average of this, the value at the 4 strain gauges. So at one end of the balance, which is the Earth side, we apply 0 degree of freedom, so it's completely attached. On the other end, we applied a temperature, a thermal load that varies with time. So we can see here on the plot that after a few seconds, we have a throw a decrease, a sudden decrease in temperature, and then slowly the balance warm up again. So here are one beam. So here is a plot of the beam strain against the time, and we can see that just 10 degrees of changes in temperature can give a beam strain of 10 to the minus 6. So we can think that, okay, it's not that much. I mean, a magnitude of 10 to the minus 6 is really small, but it can lead to an actual force error of about 25 Newton, which is not significant, negligible. So in this FE simulation, I'm going to use later for comparing my results using the method, the novel numerical method. I've got here you can see how the balance behavior throughout the time. So from time 0 to 1 hour. So at time 0, the balance has a temperature, ambient temperature of 295 Kelvin, and the thermal strain is just 0 everywhere. And then you can see that after 1 minute, the one end of the balance is really cold. It's because it's due to the very cold applied load. And after 1 hour, we can see that the balance is warming up again. So at 1 minute, we can see that at some beams, the strain is quite small. So it's about 10 to the minus 6. Again, it's not 10 to the minus 6. It may not seem a lot, but in terms of forces, it can be significant. So here I've got two plots. So this is the result of the beam strain. So I'm comparing the FE data against the thermal correction method. So the FE data are given in a dashed line, while the thermal correction method the results are given in the blue line. And we can see that the thermal correction method is following very closely the FE data, which is good. So we can see still a certain deviation. However, what we are looking for is trying to find a balance between computational cost and accuracy of the predictions, of the strain prediction. And based on these two challenges, here we can see that we kind of have a quite promising results in terms of correcting beam strain error due to temperature changes. So this is the result for two beams, beam 1 and beam 2. So at beam 1, we have an increase in terms of strain at the peak where we have a very, very small temperature. However, for another beam, at the same time, we have a very sharp decrease in terms of strain. So this is one thing. So in terms of forces, so I've got three forces here to compare against the FE data. So I've got the actual force on the top left, side force on the top on the bottom left, and the normal force on the middle right. So, and we can see clearly that the thermal correction method is following very closely the trend of the actual of the forces, whether it's the actual force, side force, or normal force, which is quite promising for us. This method is quite promising because we can, with using this one, we can correct a good portion of the strain due to induced by the temperature changes. So just to conclude, so the balanced thermal correction method provides good prediction of the thermal induced strain. For us, it is very promising for correcting balance measurements affected by the thermal strain. This method can be also widely used for other balances, so it doesn't just restrict to this balance on the screen, and it's very cheap computationally because it gives very near live correction to test. So this is for my part. So I let Manjib to present his section.
Hi all. My name is Manjib Yubi. I'm a senior instrumentation engineer here at ARA, special in strain gauge installations for wind tunnel balances. Just going to talk you through the strain gauging and wiring of this particular balance. So the 5 main stages of the installation are going to be the planning, the preparation, the installation, the thermal correction, and applying the protective coating afterwards. So for the planning stage, we were able to produce a plastic 3D version of the balance. This gave us the opportunity to have a physical 3D visualization of the balance and anticipate any problems that might arise before committing to actually manufacturing the real thing. As you can see here, the alignment and the bonding of the strain gauges was going to be the most difficult part of this process in these beams. Activities to plan were going to be the method for installing the strain gauges, positioning and bonding, confirming there was sufficient access for soldering, working out all the wiring routes to get the wiring from the various bridges on the balance to the tag boards on the front end where plugs would be fitted for model installation, and working out any wiring routes to get the wiring from, sorry, I've just said that, sorry. Identify which features needed to be chamfered and any feedback adjustments for the design and manufacturing team. Onto the preparation. So some of the preparation activities before install, we're going to be checking the balance there's no sharp edges, which could result in damaging wires, getting some chamfers and some radiuses put in on any sharp edges. And checking the beams that the gauges that were going to be installed on were not pitted and have appropriate surface finish for the gauges to be bonded onto. Here you can see I've had a sort of a pocket added whereby we'd put some tag boards in so we could split the wiring routes, which would help us find any faults or any earths during the installation. So the installation itself, we're going to chemically clean the surface areas of where the gauges were to be bonded, mark out the gauge positions, bond gauges to the surface. After bonding, doing a visual check of the gauges, checking particularly for any air bubbles on the grid surface. Check resistant outputs of the bridges, install the tag boards and wire up the bridges, and once wired, record the bridge outputs and perform a basic function check. PRTs were also installed on the balance after the strain gauging wiring. We move on to the thermal correction. In use, the balance will be subject to verified thermal effects, which can introduce measurement errors. Steady state effects can be minimized by conducting thermal corrections in the balance wiring. So we do this by placing the balance into an oven and we heat the balance to 60 degrees C. We take balance readings over time until the balance zero outputs settle at 60 degrees C. Now this is our hot reading. We then let the balance cool back down to ambient temperature and take an output reading once it's stable at ambient, and this is our cold reading. This gives us a thermal drift output. We calculate the difference in stable output between the cold and hot temperatures and use this to calculate the length of wire needed in the bridge to minimize the thermal drift. We implement the changes by adding wire, and we repeat this process until the requirements are met. And finally, after the balance has been successfully calibrated, confirming that the strain gauge process and installation has been successful, the strain gauges, wiring, tag boards are all protected with protective coating. This protects the balance against any damage, moisture or harsh chemicals that may come in contact with during manual handling or in the testing environment. I'll hand you back to Simon.
So thank you, Manjit and Huda. That was very helpful presentations. I'm just going to finish off the ARA presentation with a discussion of calibration, followed by some challenges for when we actually use balances in the wind tunnel. So we need to calibrate our balances, and at ARA we do this by applying dead weight precisely calibrated calibration weights. This picture shows our calibration facility. So the balance is in the middle inside this loading body, which is a square structure onto which weights are is supported on a rear motorized device which allows the balance to be leveled in pitch and roll, so that the calibration weights are applied purely in balance axes and there's no small angular errors as the balance deflects. Calibration weights are calibrated to international standards by a special calibration process. In the far right you can see the data logger, which is used to record all the balance channels during the calibration. And on the right hand side you can see a dead weight loading machine, which is a pneumatic device which is used to put weights on and off the balance, which prevents strain injuries on the people doing the work. So this is a standard balance that we would employ in a sort of military aircraft or civil aircraft model. The balance that we've been discussing earlier was the dual stream jet propulsion balance, which has slightly different calibration facilities. So balance calibration allows us to apply multiple known forces and measure the electrical outputs. From this we create a mathematical model of the balance which can be used to predict the applied forces and moments when we measure the electrical outputs during a wind tunnel test. The difference between the applied loads in the calibration and the measured loads on the balance is called the residual, and this is a key statistical quantity which is used to determine the experimental accuracy of the calibration. So for the dual stream jet propulsion rig, the calibration facility looked like this, slightly different. In this case, a specially designed loading frame was mounted around the balance and loads were applied using load cells supported from this calibration frame. When we come to do the actual wind tunnel tests, there are various considerations. So this is the model installed in the wind tunnel. Air is flowing into the viewer in this case, so it's coming from the front, from a head and blowing into the viewer. The model is mounted in the middle, as you can see. In this case, there's a model of a wing mounted to the side to look at wing effects. The model from the front looks like this. The nose has a fairing on it to model to create a good flow around the balance at the back end and make sure that's smooth. Looking from with the rear parts of the nacelle is what we're interested in measuring the loads on. The wing is not attached to the model. There's a small gap between the wing and the nozzle. This is looking at it from the back. So what are we interested in? We want to avoid the effects of hysteresis, and we would like to look at the electrical output and make sure that is stable over time. And we want to make sure that the balance doesn't exceed any stress limits or visually monitored to make sure there's no issues during the wind tunnel test. So hysteresis, this is when you apply a load and friction prevents it from going back to its initial position. So you apply a load manually by hand, take the load off, and then check the electrical output to see if it's returned to its original value. Typically, friction can be due to wireways, cabling that goes from live to earth on the balance, or an issue with the balance joint, the attachment to the balance. We can also identify failures of the strain gauge when we do these hysteresis checks. The other things we monitor continuously is stress. So we calculate a stress factor in the balance. We multiply the loads by the stress factor, and this gives us a a simplified version of stress in a particular region of the balance. The advantage of it being so simple is that we can actually do this continuously throughout the test while we're taking data, and make sure that we compare the measured stress with the maximum allowable stress and make sure that it never exceeds the maximum allowable stress. We can do that for various regions and structures within the balance. So this was conducted in conjunction with Rolls-Royce, and it was a very successful test. We've got some very good data that is going to help to provide better nozzle shapes during future aircraft designs. And that concludes the ARA presentation. I would like to ask if anyone has any questions.
And so would I. As chair, I'd like to ask us a seeding question, if I may. In amongst all of that you were doing there, what was the biggest challenge of all of that? I mean, the techniques that you're using are very interesting, but I understand that some will be more complex and more difficult to deal with than others. So what was the biggest challenge that you had in measuring all of these forces and things in a wind tunnel?
Well, I think that we all have a view on that. My personal answer would be it's the difficulty in installing, designing a balance that fits into such a small compact shape inside a wind tunnel model and can still measure accurate loads on the model, and also with extremely high loads. So you're talking about 2 or 3 tons of load that can be applied for a civil aircraft model. So in my view, the most difficult part of the process is the design part, where you're trying to design this structure that fits inside a model that is strong enough and accurate enough and doesn't deflect too much and has so many conflicting requirements on it. And then at the same time, in this case, we were blowing air through the middle, which induces huge thermal effects, which also need to be taken into account. I don't know if you guys have any views on that.
There's another question that I'm burning to ask, actually, because it wasn't obvious to me there, the actual load cell that you're talking about there, is that a single axis or is it a multi-axis device?
Yeah, sorry, that wasn't really made totally clear. It's 5-axis, so in a way it's 3-axis, so it's measuring axial force, normal force and side force, and then it's measuring the pitching moment and the yawing moment, so 2 moments and 3 forces. So the only thing it's not measuring is the roll effect on the balance. So that was it's a 5-component balance. We often make 6-component balances. Sometimes we only make 1 or 3-component balances as well. Yeah, depends on the application. So we're mostly interested in axial force for this because it was sort of a jet effect thrust coefficient measurement that we were interested in.
That's good, because I was in a similar position to you when I used to work at MIRA, at the Motor Industry Research Association, and we used to build very similar load cells to what you've built there for measuring engine loads and gearbox loads, probably similar ballpark in terms of loading themselves for 6 degrees of freedom. And one thing that I spent a lot of my time doing is actually looking at the crosstalk that is induced, as well as the thermal loads, which are very important, and it's a very interesting technique. How do you guys handle crosstalk measurements?
If you're talking about,
that's the effect on, say, an axial load if you put a side load on.
Oh yes, well, this all comes from the calibration. This is allowed for within the calibration. So what we do is we apply calibration loads in axial force. At the same time, we apply a varying normal force loads, and we use a multi-optimization tool to provide a mathematical model of all the balance outputs depending on all the inputs that are all varying at the same time. So we allow for the effects by applying them simultaneously during the calibration and taking them into account in the mathematical model, so that when we output say axial force from the final test, it is pure. That is a pure measurement of axial force. It doesn't include normal force. Has already been sort of taken out. and then there's a normal force that would be output separately.
Excellent.
David, we have had a couple of questions come through now from our delegates. Firstly, from Jem, can the team provide some other examples where you believe your work could have a direct and immediate impact either within aerospace or maybe wider industrial applications?
That's a good question. We've only really ARA. We've because we're a wind tunnel facility. We're mainly been focusing on the wind tunnel application, but these balances, of course, are used throughout various industries to measure loads on all kinds of things. And again, probably the thermal correction methodology that we could use has a wide-ranging applicability. I think it's used on CNC machines, for instance, to determine the deflection of the tool. So yes, I think there are wide-ranging applications that it could be used for. There's probably, I think the motor industry is probably another key industry, but they're particularly interested in loads on Formula One cars, for instance.
Or any cars. Sorry, I'd just like to interject there. So one thing that's used a very similar technique in allowing for thermal measurements is on things like measuring the mounting of turbochargers and superchargers.
You mean static tests, I suppose, yeah.
Dynamic tests out on the vehicle.
Oh, right, yeah.
Yeah.
And we've got another question coming from Alex. Why doesn't measuring force at pylon work in this case?
In this case, the actual loads that we measured were on the rear nozzle, and the pylon was also included, so the pylon was attached onto it. The wing was separate, but in this case, the actual loads measured were on both the nozzle and the pylon together. It was all one structure that was measured. You could measure loads on the pylon separately, but that would add another level of complexity, and that would be so we tried to keep it simple by just measuring loads on the whole thing. I think for other wind tunnel tests, we sometimes measure loads on a pylon that's mounted on a wing, as well as a store that's being mounted on the pylon. So both things.
And I've got one further comment from Jem. Maybe a good idea to reach out to your delegates in here if you'd like to extend the use cases of your developed techniques. So I guess if anybody is wanting to put anything back to our presenters, please do email me. It's info@e-i-s.org.uk. I'll put that address in the chat. And if you do have any further questions, please speak up now or add them into the chat.
I have another one actually. Seeing your plastic model right at the beginning, it reminded me very much of quite a few years ago when we used to do photoelastic methods. Did you think of maybe doing any of that for your strain gauging?
So you're measuring the forces by looking at.
Yeah, you make the plastic that you used is probably just plastic. I don't know which one it is, but you can use various plastics that you can put polarized light through, and as you deflect and put loads onto the plastic device itself, it shows you pretty much the strain and stress patterns all the way through the device. Admira have used it a few times for making very bespoke load cells that have to fit in a particular space.
That sounds really interesting. I might have to investigate that. I know
Look
that
at photoelastic. I might go into the AIS presentation.
The only other related technique that I've heard of is using optical fibres, I think, instead of strain gauges. You mount those inside a balance. I believe that's an ongoing sort of technology that's being developed in universities at the moment. I think that might have certain advantages.
Amazing how things come around, usually on about a 10 to 20 year cycle. I've been around long enough to know that.
Yeah, it's quite common that these ideas we think of are actually been around a lot longer than we think.
Okay.
I've got a further question from Jacob. Is the temperature correction method still valid once the model is bolted to the load cell and thus acting as a heat sink and changing the temperature gradients?
Yes, I think that is a good question and something that we will be looking at. But I think the actual methodology would just need to be extended slightly if necessary. But I think ultimately most of the thermal effects are localized within the balance. So that is probably the main thing. That when you're looking, what we're looking for is gradients across the beams, temperature gradients, and this is what causes the strain. So what temperature the rest of the model is at is not necessarily going to affect those local variations in temperature.
How quickly can the method cope with changes of temperature? I'm thinking now about the fact that with what you have there, probably it's a nominally steady state with slow changing temperatures. But if you were dealing with, say, like a car engine or such like, the temperatures vary quite rapidly.
I think the actual methodologies would be able to model any sort of thermal changes, but the actual structure of the balance wouldn't actually vary that quickly. So whilst you might have a huge heat input, well, I think in our case the heat inputs are quite low, but yes, in the case of certain other applications I can see where the heat load would be much greater and the structure would respond a lot faster. I think that there is an extension to the current methodology which would take into account the time domain in a more detailed way. That would be further work.
Great. Have we had any other questions, Sarah?
Nothing's come. Oh, hang on. Well, there's appears to be typing going on, but nothing's come through yet. So perhaps if we just give it a little bit longer before we bring things to a close.
I think the DSJP rig that we developed has some unique characteristics in terms of the way it handles air blowing through the middle of it and the thermal variations that we're now compensating for. That's fairly unique, I think. Most of our balance have air flowing over the actual structure.
I've got a further comment from Jacob here. Maybe you could use an insulating separating barrier to reduce the effects of the model heat sinking, i.e. therefore maintaining the validity of the simulations that were developed in isolation. Just an idea.
Yeah, that's a very good question, and things like that have kinds of metal, steel. The current balance, just to be clear, is not made out of plastic in the actual model. It's made out of high tensile steel. But you can actually get kinds of steel with lower thermal conductivity. We've looked at structures that surround the balance made out of that kind of steel. So it helps reduce thermal load into the balance.
Yeah, so my suggestion about photo E with the plastics is for deciding on where you put strain gauges and the orientation and optimizing orientation.
Yeah.
Photo E is not something, well, sorry, you can do it, but not on anything that's actually got that much thermal changes.
Right, okay.
But it's a very good technique from quite a few years ago. It's a good whole device visualization.
That sounds interesting.
It's a very good way of optimizing effectively your 6 degrees of freedom as strains on the surface of some complex device that you are converting to a load cell. So
Right.
you can show you where, even easier than with FE, because you're probably making it anyway.
Yeah. I see. At the moment, we use some sophisticated thermal analysis tools, so that might be an easier way of doing that.
But it's a way of doing it, unless I say it's easy.
A way of doing it, yeah. It's an interesting idea, though.
Yeah. It's quite an old technique that keeps coming up. And,
yeah.
but in this day, especially with 3D printing, I could see that it could have its time again, because now you can make the complex shapes quite quickly. You don't have to machine them. You could actually 3D print the shape up.
Yes, this has been really
useful. Then look at the photo of the whole device in 3 dimensions. Yes,
we use the 3D printing technique to create a physical model that we can look at and decide where to put the gauge, sort of how to wire up the gauges.
Yeah.
And it helps to actually see a thing on a table rather than something on a computer screen. Sometimes it's much easier to visualize.
Sometimes just having the 3D device in Perspex, which is one of the units, because it works very well with Photo E, is that you then put your polarized light through it, the view with the view through a polarizer, and you can physically just put some loads on it in each of the directions, and you can see the strain patterns moving across the surface exactly the same way as they would do on the real device.
Oh, right. That sounds really interesting.
It's a whole body device. It's very, very good. Look it up.
Yeah, I will do, definitely.
For you guys being so young, and the young engineers there, it'll be in your history books. But it's something I was doing for real some time ago.
Oh, wow.
Well,
on the list there might be a couple of people that know what I'm talking about from the list.
I think that's it from questions from our audience, David. So I don't know if you want to perhaps
I'd like to say
now.
I'd like to say thanks very much for a really interesting topic, quite up to date, and I think it will help in a lot of other industries. The automotive industry, especially, actually, because we do measure a lot of things in a similar manner. I mentioned a few on things like exhaust systems and flow systems, input systems. And one of the biggest things that we do have is that there's not much space and there's a lot of very high temperature gradients. So very, very interesting. I hope everybody else thought it was as well. Thanks very much.
Thank
you.